All right, so tonight we're going to be talking about a variety of things, but a lot of what we're going to be talking about tonight are basis, forming a basis for a basis for a matrix, or for, this forms a basis for R3 or R2 or Rn or whatever it is. We're talking about that a little bit tonight. We'll be talking about subspaces, particularly three important ones: the row space, column space, and the null space. And trying to get a handle on that. We're going to talk a little bit more about rank tonight, and then kind of see where the whole piece fits together. So a basis, for a basis to exist, there's two things that must be true. Okay, two things that must be true for a basis to exist. Okay, so a basis is a collection of vectors and the definition is on page, oh, I lost it, darn it, there it is, haha. No, that's not it. There, a basis for a subspace is a set of vectors that spans S. So first of all, so a basis for a basis for subspace S. And we're going to define subspaces again in a little bit here. S of Rn is a set of vectors that is A, linearly independent, and B, span S. Okay, so if both things are true, then those collection of vectors form the basis for a subspace. Okay. Now you're like, well, that breaks the question, Jay. What is a subspace? Glad you asked. So we'll define that sucker as well. Nice. Okay. So a subspace, by definition, right here, a subspace of Rn is a collection of vectors. Any collection of any collection S of vectors in Rn such that the zero vector shows up. The zero vector must be included. Okay. If U and V are in S, then any linear combination, then U plus V must also be also in. Now what the big kids say, that means it's closed under addition. Okay, so for instance, if you have whole numbers, the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, da, 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 forever, or a whole number plus a whole number will also be a whole number. You're not going to get a fraction, you're not going to get a negative, you're not going to get an imaginary number when you add them. That's we see that means it's closed under addition. Also, U is in S, and C is as a scalar. Then C times U is in S. All right, that means, what does that mean? It means it's closed under scalar multiplication. And what does that really mean? It means that gives us the ability to not only do scalar multiplication. There it is. Good. What that really gives us the ability to do then is take C1 times U1, or times U, plus C2 times V. This will also be in S. Why? Because this is in S, this is in S, and the sum is also in S. Okay? So that's what kind of makes it neat. So if that's true, right, any collection of vectors where it's true, that will also make it work. Now, we're going to look at what does that mean a little bit more in depth. I hope you're going to see some examples of where that comes into play and how exciting that is. So first off, I'm just going to ask you this question. The question is this. Can you give me, or let me put it this way, do these guys form the basis for R3. Okay? So the question is, does 111 102 110, does that form a basis for R3? Question mark. Will it generate R3, in other words? Well, I don't know, Jay. Yeah, here, I'll help you out. So what we're going to do is, if that to be true, keep this in mind. For that to be true, we need to be able to take this matrix, which of course is just the collection of those vectors, and multiply them by some A, B, and C, and we should be able to produce every single X, Y, Z out here. Are you with me? Every single one of them. Okay? If that's true, then every X, Y, and Z, then yes, it is the basis for R3. If it's not true, then we've got problems. Now, how are we going to try this? Well, what we're going to do is we're going to create an augmented matrix. Let's try this thing. Now let's do a little row reduction here. So R1 minus R2. Oops. Try again, stupid. 1 minus 1 is a goose egg. 1 minus 0 is 1. 0, A minus B. And then R1 minus R3. Okay, now let's keep reducing, shall we? So let's do a little, we do row 1 plus row 3. That'd get rid of that, so that would give us 1 plus 0 is 1, 1 plus negative 1 is 0, 1 plus 1 is 2, and then A plus C, A minus 2A minus C. Okay? And, oh, that's really funny. By the way, is there any reason why I did it that way as opposed to using the middle vector? No. Matter of fact, I think I'm going to go back and do it just so I don't screw up my notes, or just don't screw up looking at my notes, put it that way. But the idea is can I do elementary operations on any of those guys? Yes. In other words, will I always get the same exact answers out? No, I won't. Does that bother me? Not really. So this is going to be A minus A minus A minus A minus B, so it's going to be A minus A plus B, so it's going to be B. And then I'm going to have the middle one. I'm not going to leave. I'm not going to touch him. And for the bottom, I'm going to do row 2 plus row 3. 0, 0, 1. And then if I add these, I get 2A minus B minus C. 2A minus B minus C. Which is, yay, that's what I got on my thing. Woohoo! Now, what does that mean to me? It means this. Hey, let's let A equal something. Let's let A equal, I don't know, 2. Why not? Let's let B equal, I don't know, 1. And let's let C equal 1 just for a good time as well, I guess, because why not? If that were true, look what would happen. Okay, look what would happen. Okay, if I plug that in there, I'm going to get 1. And I'm going to get 1. And I'm going to get 4 minus 1 minus, I'm going to get 2. That's right. Okay. So what does that mean to me, Jay? What it means is this. Come back up here. If I plug those values in that I just got, I'm going to get X, Y, and Z values. So 2, 1, 1. Now those are completely arbitrary choices that I made. So look what it's going to get. I'm going to take this row times this column and get 2, 1, 4. That's my X value. I'm going to get 2, 3. That's my Y value. And I'm going to get 2, 2 is 4, 4. That's my Z value. And a different selection of A, B's, and C's will produce different of these. And in fact, they'll produce every single stinking possible that triplet of X, Y, and Z. Hence, we can say that it does in fact form the basis for R3. Okay? Now, here's a different one here. This is interesting. Does this span that I'm going to show you, this, again, collection of vectors, Does that form a basis for R3? I don't know. Let's find out. Remember, if it does, they'll be linearly independent, which means I should be able to get down to 1, 1, 1 on the diagonals, zeros everywhere else. If that's not true, what does that say? It says they are not linearly independent. So if I do 2 R1 plus R2, I will get -1, 4, -6, Then I will get 0. I'm going to get 8 plus 1 is 9. I'm going to get -12 plus 3 is -9. And I'm going to get 2a plus b. That's hot. Now let's do let's just do R1 rather plus R. Darn it. And that will give me 0, 1, -1, a plus c. Oh dear. Oh dear. So if I just did R2 minus 9 R3, look what would happen. Interesting. Interesting. Now look what happened here. First of all, I got this 0 line here, which means that somebody was linearly dependent, which means that this cannot form a basis because, wait, they're not linearly independent. Okay? That's number one. Number two, what does this look like? This actually is kind of exciting. This guy right here looks very similar to this right here, does it not? And what is that guy? That's a plane. Is a plane three-dimensional? Well, no. Because what's happening here is you've got a vector going this way and a vector going this way, but where are they? They're in the plane. Where's that third vector at? It's also in the plane. That make sense? It's also in the plane. Now, it's at this juncture that I'd like to stop for a jiffy here and talk about something that's pretty slick. And that is the idea of what is called the null space. And so obviously if it forms a basis for the whole R3, that's great. But in this case we only formed a basis for R2, that it's a two-dimensional thing. It has length and width but no depth. Well, then that third dimension, you see, must be the null space. Does that make sense? In other words, R3 would be three-dimensional. It would fill up the entire space. But here we're only filling up a plane. We're only filling up a plane which has length and width, no height. So our null space then must be somehow related to this. And so I'm going to rewrite that original equation here. And I'm going to set it up, and then I want to just kind of just tell you this right here. This is how this works. It's pretty exciting. Check this out. Right? Now, how did we solve this equation? Because when I do this, I have it equals the null space. When I find the answer to this question, x, y, and z, when I find the answer to these questions here, and x shouldn't be x, y, z, it should actually be a, b, c, I guess I should put it that way. I'm looking for constants or coefficients that would make this true. Okay? The values that make that true form our null space. Okay? Now, we know how to solve these. We have a variety of ways in which to do it, but I'm going to go ahead and just use that augmented matrixy look again. By the way, if you're thinking back to differential equations, solving homogeneous solutions, this is in essence what you're doing here, right? Homogeneous systems of equations in essence. So let's do 2R1 plus R2. And again, I cannot stress to you enough that you see it different than me. Some books always go on and on about how, well, yeah, we're always multiplying by halves and quarters and stuff. And one of the books that I have that I use as a reference just for some extra problems, constantly doing it. It annoys the bejesus out of me. It's 8 plus 1 is 9. And you're like, hey, isn't this the exact same equation as last time? Sure it is. Sure it is. But what I want you to see on this deal is it's kind of exciting here in a second to kind of take a look at here. We're looking for values that'll solve this guy. Somewhere I got off a little off kilter. Hang on. Let me pause myself. I'm going to find my notes here. Okay, I guess we're still here. So then these obviously again cancel out. And so I end up with this. -1, 4, -6. Right. Okay, that's kind of neato, I guess. Alright, so here we are. I'm going to divide this next row by 9 just for a good time. And just for a good time, I'm also going to go ahead and get these down to 1, get a 0 here, just for fun. Okay, so to do that, I'm going to do R1 minus 4R2. Cool. What you can see is we've got a pivot here and a pivot here, right? That's where we're in reduced row echelon format. No pivot in this column. These, if you look at these first two columns, you know, they were fine by themselves, but this last one's a little weird, a little strange right here. This guy right here. In other words, we had 3 variables, but we only had 2 independent equations. So what does that mean to me? Well, it means that you can't obviously, first of all, it means it does not have full rank, number 1, right? What does it have? It has rank 2, because we have 2 equations, right? I mean, that's clear, which means we have a free variable. In other words, if you were doing x, y, and z, x, y, z, then your z variable, quote unquote z variable, would be what we say would be free. Okay? And we want to look at this guy here. And I want to show you something. -2, -1, and then what's that negative? Oh yeah. By the way, for instance, this is interesting. The example that I used this for, that I used with this, came out of another textbook. And check this out, right here. They had this. Okay, maybe not. They had this positive and this positive, and then they had, that's it. They had it just like, and then they had it. So we had it. That's how they had it. And then like, well, is that any different than the way you had it, Jay? Not really, other than we want to see our 1 up there on the first column. Okay, so just be aware of that. Other than that, it's not a huge concept. Just be aware of that. But sometimes you can actually see where they. Some books will go through and will reduce things a little bit differently, change things up a little bit. But let's look at that vector right there. So 2, -1. Well, don't I need a 3-dimensional something? Okay, don't I need some kind of 3-dimensional something? So what we're going to do is we're going to just add a 1 to the bottom of this guy here because, well, for several reasons. I'll show you which right now. If this was z, this is very much like 2x minus y equals z kind of a thing, right? And you can kind of think of it like that. That's one way to think of it. The other way is just that you need a 3rd dimension, so you just add another dimension to that. This guy here should look vaguely familiar to us. And if you don't believe me, let's come back up here and let's look at these first 2 guys, these first 2 vectors. I'm sorry. Eesh, I almost screwed that up. Whew. Let's look at the first 2 vectors, these guys here and here. Holy crap, that had been embarrassing. 1, 2, 1. And what did I say the other one was? -1, 2, 1. and 4, 1, negative 3. Oops, 4, 1, negative 3. I, J, K. What are you going to do, Jay? I think I'm going to use the cross product, and I'm going to get, oh, I hope this works. Oh, I hope this works. Oh, cross your fingers, Jay. Can you do it? Are you smart enough? Oh, my neighbors are loud tonight. Hold on a sec. Alright, I'm biffing that up, so I'm going to keep moving. I'll come back to it maybe. I was actually got a little ahead of myself on that deal anyways. I didn't really want to do that one right off the bat. But suffice it to say that null space, what it should have done, and I'm not making it work out right, what I had was a plane. Okay? The idea here is, and I'm biffing it somehow, and I'm failing to see what I'm doing wrong. I thought I had it in my notes right, but it's not, apparently. So you had that plane, you see, those vectors are in a plane. If you're not in the plane, where are you? Well, you're sticking out of the plane. Right? You're coming up out of the plane. Wait, you mean like the normal vector? That's right. So in theory, that should have come out to be the normal vector, normal to the plane, and those deals there. That's where that guy should have been. And it should have formed a basis for all normal vectors, and whether they go into or they go out of, and how long they go, because they could be any scalar multiple of the guy, whether positive or negative. Okay, somewhere I biffed up and I'm failing to see it, so I'll keep searching here, but I want to keep going. I want to get this over with so I can get to bed at a reasonable hour tonight. Right, so let's say this B, this is a set of vectors here, that's this spanning set here. Okay, I've got this span of vectors. Okay, the question is it a basis for R3? Yes or no? Well, here's the question right off the bat. If you look at this, clearly this guy and this guy are independent. There's no way you can add them together. And this guy here, they're all three linearly independent. You can tell that basically by looking. By the way, the dimension for R3 is, of course, R3. I mean, duh, right? It's a 3 by 3 system. So all I have to show these guys are truly independent. I can tell that by looking, but if I can't tell by looking, we've done this before. We make an augmented matrix, and we see if we can get these guys to, cancel out. If we can get them to cancel out, or that is if we can find A, B's, and C's where they would cancel out, then of course they would be dependent, but they're not. So if I look at this deal here, right? All right, so let's see. Let's do what do we do? R1 minus R3. So of course I get an equivalent matrix of 1, 1, 0. And then of course I'm going to get 0, 1, negative 1, A minus C. And then let's do, while we're here, let's do R1 minus R2, which would give me 1, 0, 0, A minus B. And then let's do row 3 minus row 2. And so it'd be 0, 0, negative 1. And that would be A minus B minus C. Okay? Now we're in reduced row echelon form. There it is. Perfect. Whatever. Now, if you look at this thing here, what can be done here? All right? Well, if you do this, okay, if you do that, then, well, let's think about that. So it'd be, if you let A equal 5, let's say, okay, and what did I do? Actually, I just know what I did. I did A equals 2, B equals 1, C equals 2. look what ends up happening. If you pick these numbers, for instance, 2 minus 1 is 1, 1, and 2 minus 1 minus 2 is negative 1. Okay? So the question is, when I do this, what I found is I found those guys there. And again, same thing as last time. If I plug those back in and I multiply it, the question is, when I plug these values in, times 1, 1, 1, negative 1, right? I'm going to get x, some x's, y's, and z's. And of course, if I change these guys, which change go into there, well, these change this, these guys then go into here, I should say. These guys affect these guys, and it will actually can be such that you can produce everything in the plane, or everything in the R3. Now, if you're not sure of that, another way to think about that is this. If they're independent, what should happen? Well, if they're independent, right off the bat, you should be able to get a determinant to show up, yes? Now think about that. Why is that? Because if this was your A matrix and you were going to solve for it, you'd have to be able to do the A inverse. For this to work, they would have to be a consistent system of equations. And for a consistent systems of equations to show up and to solve, I would have to be able to do A inverse. Okay? It'd have to exist. And what does an inverse have in it? It has a determinant, 1 over the determinant. So if you're doing this by hand, it's 1, 0, 0, 1, expansion by minors. So 0, 0, 1, I, right? So 1 is my determinant. Okay, that is my determinant. Ta-da! 1 is my determinant. The fact that it exists at all says that they are linearly independent. So they're linearly independent. There's your basis matrix. Okay? And your basis for your R3. Okay? Here's another one here. Don't want to spend a ton of time on this one. Are these guys a basis for R4? In other words, if you have these four guys right here, could you pick some A, B's, and C's that would give you everybody in R4? And I think you could. So if you chase this all the way down, you finally get down to a situation like this, where it's 1, 0, 0, 0, and it becomes C plus D minus A plus B over 2, and 0, 1, 0, 0, A minus B over 2. 0, 0, 1, 0, it's A minus C over 2. And then 0, 0, 0, 1, A minus D over 2. If you pick A, B, C's, and D's, you can get it to work, and that's great. It works for everything. Also, you can find the determinant of this guy right here. The determinant of that guy is 8, or negative 8. And the fact that it exists at all says that they are linearly independent, therefore forming the basis matrix, the basis for R4. Okay? It's just another way of coming about that. Okay? Here's a question for you. This one out of the book, or one similar to it, I guess. Okay, here's a matrix A. And then here is a vector 3, 1, negative 2. And the question is vector B in the column space of A? Okay, that's the question. Well, here's the deal. B is in the column space of A if and only if there's a vector X such that, that's my own little briefing there, such that AX equals B. Okay? That's it. So what do I mean by that? Well, I mean by that is this. 1, negative 1, negative 2, 3. 1, negative 1, 2, 3, 1, 2, negative 2, negative 2, negative 2. Okay? If I can get this down to a reduced row format, and it works, then yes, in fact, it is in the column space. Okay, so here it is. So it's R1 plus R2, of course. And 2R1 minus R3 gives me this guy here. Okay, I'm going to change these guys to 1 and -4, if that's okay with you. I'm doing it anyways, I don't really care. Boom. Okay, and then I went row 1 plus row 2. And I ended up here 1 0 -1 7 and 0 1 1 4 0 0 1 -4. You can all see what's going to happen now. We're going to do a little row 2 plus row 3 action, and of course you end up with 1 0 -1. Oh, I should have done that too at the same time. Let's do that in a second. Let's leave that blank for a second. Let's do the middle row. It's going to be 0 0 0 1 0, I'm sorry. And then 0. No, 8. Because I'm doing row this guy. I'm sorry, this. I am going to do row 2 minus row 3. That's right. So yeah, there it is. And then 0 0 1 -4. And then for the top row, I'm going to do row 1 plus row 3. So it's 1 0 0 and 3. Is that right? Yay. What does that mean, Jay? I'm glad you asked, friend. It means that 3 times that first vector plus 8 times the second vector plus, or minus rather, 4 times that last vector is equal to our vector that we're interested in, which was 3 1 -2. So what that means is there is a vector 3 8 -4 such that gives me the perfect linear combination of the 3 basis matrices there, or the 3 bases for my vector of my matrix. If I take that and multiply, I get 3 minus 8 -5 minus, 3 minus 8. Come on, Jay. Yes, 3 minus 8. Oh, this should be a -2. Huh? Wait. Yes, that should be a -2. So this is 3 minus 8 plus 8 is 3. -3 plus 16 is 13. Minus 12 is 1. 6 minus 16 -10 plus 8 -2. Yay! It works. Woohoo! And that's how you would show it is contained in there. Okay. Another example of that. Here's A. B. The question is B in the column space of A. 1 2 1. Let's find out. I don't know. And so, of course, just like last time, set it up as an augmented matrix. When it's all said and done, you end up getting down to this. And so the answer is nope, sure is not. Okay, sure is not. And that's because this last guy goes away. What does that mean? It means those guys, it means it's not in the, means they're not, well, it means they're not linearly independent, number one. But it's not in the system is what it's not doing there. Okay. So these guys over here, you can rewrite those rows or columns rather as dependencies of each other. So they canceled out and they went away. That would only be not true if the original A matrix was what? If it had full rank. So this guy does not have full rank. It has rank 2. How do I know? Because I ended up with 2 rows that had anything left in them when I was all said and done. Okay, but again, it's not in there because this is a three-dimensional guy. It cannot be in there when I only have rank 2. Okay, you can't have a three-dimensional vector in a system that only has rank 2. That's not going to cut it. So no, it's not. Okay. Here's a couple of things to think about, and it's kind of, it sums it up a little bit. If S is a subspace of Rn, okay, the number of vectors in a basis for S is called the dimension of S. Okay? And so the row and column spaces have the same dimension. This will always be true. Row of A and column of A have the same dimensions. We're going to do a couple of those in a few minutes. It's going to be pretty obvious. Clearly, if you had one that was 3 by 3, it was full rank, then obviously they're both 3. If it was a 3 by 2, well, clearly the best you'd ever hope for is 2, and we'll talk through that in a few minutes. The rank is the dimension of the row and column. So these guys right here, the dimensions of those guys is equal to the rank. Is equal to the rank of A. I want to clear that up a little bit more as we go along. Yeah, for any matrix A, the rank of A is equal to the rank of A transpose. Doesn't change anything just because you flipped it on its side. In other words, the same thing can be true if you have 3 equations with 2 unknowns or 2 equations with 3 unknowns. It's all the same. You still can't be done. The most you can get out of that is a rank of 2, regardless of how you set it up. Okay, the most you can ever do. The nullity, weird, of A is the dimension of its null space. Okay, it's also, and then you write that as the nullity of A. That's how you write it. And this is pretty cool. So rank nullity theorem. It's about the easiest thing on the planet. The rank of A plus the nullity of A is equal to n. What do I mean by that? If you have A is an m by n matrix, there are n columns. That means n variables. Right? Well, if you have full rank, well, the best you can hope for is a rank of n. Is that right? A rank n is the biggest you can ever hope for, right? That's the biggest you can ever get, because, in other words, if this was like a 7 by 6, then the most you could ever have is a 6 rank in that system, okay? But that's the idea behind those guys. Now, if it's 6 by 6, of course, is that's the idea of that guy. So the rank of n, so the rank of A minus or plus the nullity of A is equal to n. The idea here being you're going to have free variables. The number of free variables is the nullity. That's the game. Okay, so we'll go along. So then this guy here plus how many free variables you have equals n. We'll talk more about that as we go. I think it's easier to see when you actually do a problem of them. Well, like for instance, this guy here. Huh. Let's do him. All right. So, let's do this. Suppose you had this guy here, which is number 18 in your book, and it asks to find the row space and the column space. That's what it asks us to find. Let's do row first. Hey, is it the same thing we always do, Jay? That's right. Let's do little reduced row echelon stuff, because why not? That's always a fun time. Here's our row equivalent matrix. 0, -4, -2, 0, 2, 1. Is that right? 0, 2, 1, I think. I feel like. It feels good to me. Okay, and then we get a little 2, R3 plus R2. It's going to give us 1, 1, -1, 0, -4, -2, 0, 0, 0. Okay. Right off the bat, what does that tell me? Not full rank. You with me? We are losing an entire row right off the bat. The dimension of our row space, right, is equal to 2. Okay? In other words, there are 2 non-zero rows here. Okay? Now, fair warning, at some point, some people might be tempted to say, well, that's it, we're done now. Not so fast, homie. Not so fast. I'd like that to be a 1 right there. That's what I'd like it to be. So I'm going to multiply everybody here by -1/4, I guess. And that's going to be kind of gross, but life goes on. And 0, 1, and -1/2. And then 0, 0, 0. Now I'd like that right there. I'd like him to be a 0. Thank you very much. And to get him to be a 0, obviously I need to do row 1 minus row 2. So it's going to be 1, 0, -1/2. And I'm going to get 0, 1, -1/2. And I'm going to get 0, 0, 0. Okay? Okay? Now, it's at this juncture right here, you're like, oh, well, that's pretty cool. Oh, don't tell me I did something stupid. No, I'm not in the mood for this. Should be 1.5, I think. I think that should be 1.5, if I'm not mistaken. I'm going to go back to here and try to quit being fancy. I was going to be fancy right there, but I'm going to see if I can fix that. Because I want it to look exactly like mine. It does and it doesn't, okay? It does. It looks just like mine. It looks like a multiple of mine. Is it a big deal? It's not a big deal. Because we know that those vectors are just products, so you could always multiply them by a scalar. Let's try this. I'm just going to do 4R1 plus R2. That's what happened. I shouldn't have minus. That's what it was. So I was right. It was -1.5. But here we go. This is what I had on my paper. I had 4, 0, -6. There you go. 0, -4, -2, 0, 0, 0. Now, if you want, you can divide everybody by 4 up on top. You're going to get 1, 0, -1.5. And you get 0, divide by 4 here. You're going to get 0, 1, -1/2. Or +1/2, right? Right? Cool. And so this is what I actually wrote down for mine. My basis matrix, my row space, what I was looking for was a basis for my row space. So for my row space, this is the answer. So the problem literally states it this way. It says, give bases for the row of A. This is the basis matrix, the basis vectors for the row space of A. I could just easily have used these two guys here. All they are is multiples of one another. So when you go back and look at the back of the book, double check to see if you just went a step farther, reduced it further than they did, or vice versa. Don't freak out. Okay, don't have a fit about it. Okay? In either case, that's just fine. Now, good news, you're like, Jade also says, hey, let's go find our column as well. Well, okay. So the column space is even easier, for God's sakes. Now remember, we need to be in reduced row echelon form. This guy here and this guy here, we have what are called pivots, yes? This one doesn't have one. There should be something here, but there's not one here. Now, what does that mean to me? It means that we're going to be looking at this vector, but not quite, and this vector, but not quite. So to find our column space basis matrices, or basis vectors, what you're going to do is you're going to go the first two vectors of the original problem. And so they are 1, 1, 1, 1, 1 and 1, 5, negative 1. But what about that last? What about it, friend? What about it? This guy here is a loser. Okay, he did not have a pivot. We don't get to include him. Again, let me just say, this was a 3 by 3 initially, right? But it does not have full rank. It only has rank 2. Okay? Well, if it has rank 2, what's the nullity? I don't know. Yes, I do. The nullity is 1. Why is that? Well, you've got two variables that have two equations and two full unknowns. What I do not have is I do not have that third variable. That's a free variable. That's the nullity of this guy. Okay? And yeah, all right. And then it also wants me to find the null space for this vector of A. So to find the null space of A. Okay, so I'm going to do that down here. Let me rewrite the problem. 1, 1, negative 1, 1, 5, 1, 1, negative 1, negative 2. Just a moment while I fix something. Okay, so I'm back. So we use these two guys for our column, or we use the first two vectors, I should say, for our column space. So what I need to do here first, I'm going to go ahead and multiply it, divide everybody by 4, and it's exactly what I had before. It's 1, 0, negative 1.5, and 0, 1, half, and 0, 0, 0 still. Now, we did not use this fellow before, yes? So our null space will be given by negative 1.5, 1 half, and now before we get carried away, we're going to go ahead and multiply that top one by positive. We're going to multiply this guy by negative 1 rather, to change the signs on that guy. Always want that top one to be positive. And then we're always going to add a 1 to that bottom guy down there if there's not one there already. Okay, again, the null space, there will not be a null space, you see, if what? If this thing was full rank, there wouldn't be a null space. You see this? Because we'd be generating everything in R3. Well, what would be left off? Nothing. The only way we're going to get a null space is if we are only spanning 2 dimensions. We're creating a plane, and so the null space is everything sticking up out of that plane. That makes sense? And so this guy right here, you see, should be sticking up out of that plane that we've created on the in the previous stuff. So just be aware of that. Let me pause one more second here. Check me out, yo. We said that these first, that these first two columns were our bases, yes? So watch, but we said they only span in 2 dimensions, meaning that I can form a plane by them. So if I took them, I did a cross product, I'd get, what is this guy here, what's called the normal vector, yes? We know that it's orthogonal to the plane, which means it's not in the plane. Well now, look what I got here, friend. Suppose I times it by negative 1. Cool. Then I get this fellow here. And then I suppose I times that by negative 4. I would get, or by positive 4, I'd get, check it, negative 6. 2. Yes. And what is going on? Negative 4. Positive. What? Oh, that should be positive. No. Well, whatever. I should have come up with the same thing. It should have been positive 4. So somewhere I messed up somewhere. Where's my original? This, and that. I flipped them. Whatever. The point... Okay, I'm messing something up slightly ever again. But my point is this. The null space, in the case of this deal here, I have a vector here and a vector here. I'm going to figure that out in a second. It's going to really irritate me. It's create a plane. Those two vectors have created a plane. But they only span in 2 dimensions. So the third dimension, right, which is sticking up out of it or into it, whatever, if you prefer. The only difference, of course, being what you multiply by, positive or negative. That would be the null space. Something's a little screwy on this, and I'm getting a little irritated of it. I was thinking about that for a minute. That's true, yes. So if I multiply by -4 right off the bat, I would get -6, +2, -4. Something is not right there. Something is not right. I think it's on that guy right there. Alright, well, I'll continue working on that and let you know what I get for an answer on that. Okay? But that's what I want you to understand about the null space. Not so much the, you know, oh my god, look at me, I found the null space. What does it mean? I found the null space. What does it mean? Well, I'll tell you what it means. In this case, it simply means, okay, it simply means what, so if those two vectors are in the plane, it's got to be a plane sticking up out of the plane, because two-dimensional plane, that third dimension, because we had a something by 3 matrix, the third variable was free, therefore we have to be sticking up out of it. I'm messing something up on my algebra there, and I'm getting a little irritated of it. I'll probably try to post an addendum later this week or tonight if I get tired of it and figure it out in a minute. Okay, here is this matrix. It's a 3 by 5, which of course means the most rank it could ever have is 3. Am I right? That's the most it could ever have, because obviously 3 equations, 3 unknowns. I mean, that's all you could do. So this is, we're over processing variables wise. I cannot solve for all 5 variables. It's just physically, it's impossible. Okay, so think about that for a minute. So if I do this, and I think I did R1 plus 2 R2s and R1 minus 2 R3s, and of course then I ended up with this 2, -4, 0, 2, 1, 0, 0, 2, 6, 7, 0, 0, -2, -6, -7. Oh, what? Shut up. 2, -4, -0, 2, 6, 1. What are you doing? Oh, sorry, that one jumped up from the bottom, next row down. And then 0, 0, 2, 6, 7, and of course a set of goose eggs. Nice. Okay, so what do we have here? We got a dimension for the row space. For the row space, we have a dimension of 2. The dimension is 2. Okay? Meaning that our rank is 2. That's all we got. Now, if you look at this, we're in echelon format. Okay? And so when we do this here, so you're thinking about this problem. Dimension of the row space is 2. Well, what does that mean then? The nullity has to be what then? The nullity has to be 3. How do I know this? How do I know that? I know that because there's 1, 2, 3, 4, 5 variables. N is equal to 5. If the dimensions is 2, which means the rank is 2, 5 minus 2, the nullity is 3. That's it. That's all there is to it. Now, while I'm here on this guy, now, could I go a step further and eliminate and do a few more things with this here? I suppose. But in reality, my vectors for my row space are as follows. My basis vectors would be this guy and this guy. Okay? It's the only non-zero rows there that are left. That's my basis. Now, you'll notice that this one has got a pivot, and this one's got a pivot. Do not screw that up. It's this guy because he's got a pivot. In other words, remember, 2 is that leading one. You come down to the next one, where's the leading one? It's in this column. It's that column there. So, what you want to do is go find the very first vector, which is 2, -1, 1. And the third vector, which is 0, 1, 1. These two guys here you can use to generate everything else. And again, what is this guy here? Yeah, there you go. So the dimensions here again is 2. So that is the basis for the column vectors, for the column space. Okay. Well. And let's see where we off here too. Yeah, I already did that one. Cool. So I will be posting a 3.6 video later tonight or maybe tomorrow. I haven't decided when yet. We'll see when it gets done. There will be a kind of a review page coming out late this week for you can study for the test on. I'll try to get 3.7 out a little sooner this week as well. So it'll be everything up through 3.7, excluding, what did I say, 3.4. That will not be on the test. Okay? I guess I can show you this. The reason I don't like to do that LU business is this. Simply put, if you had this equation, obviously it has an answer. Number one. Number two, you look like an idiot using matrices to solve it, but whatever. Equals 9, 7. Okay? Now, I'm telling you right now, this is A. I'm going to multiply this sucker by A inverse. And I'm going to do A inverse right here. So my answer literally is X equals A inverse B, if this is the B matrix. And that's it. You're done. Bob's your uncle. Let's stop. Why are you going any further? Okay? But you can jump through some hoops on this guy, and you can rewrite this as a product of two other matrices, L times U. And then times X is equal to 9 and 7. Now, that's great, but it's stupid. No one does it this way. I mean, no one in their right mind would do it this way. That's why I don't bother to teach it. Now, turns out that the 89 will actually do the LU breakdown for you. And it's in here somewhere. If you come up here and find it, LU. This is weird because you're like, wait, what's going on here? I don't understand what it's doing. I didn't either. I had to do some reading to figure out exactly what it was looking for. Because I've never done it before in here. I remember doing it back in the day. Because I had a teacher that just said, by God, I'm going to teach it regardless. And whatever, I guess. Uh-oh, no, no. Oh, no. There we go. And then comma, and then you're going to do alpha L, comma, alpha U, comma, alpha P. And then you just go alpha L. So 1, 0, 2/3, 1 times U, which is, if you just go alpha U, 3, 2, 0, and negative 7/3 equal, or times X rather, equals 9, 7. Quit doing that. 9 and 7. Okay? That's all there is to it, man. Now you're like, oh, well, what does that do for me then? I don't know what I'm doing here. Yeah, sure you do. So it turns out, and this is back on page, I'm just going to run through this. This is how you solve it. I don't do it this way. I would never do it this way. I've got better things to do with my life than to do this. So what you're going to do is you're going to treat Ly as if it were B. Okay? So L times the y vector times this vector over here is equal to B. Okay? And where's that at here? So L times y is some B value. Okay? And so, in other words, you got some y1s there. Okay? And so, the idea being is it's y1 is equal to 9. Okay? In other words, we're going to treat this guy as if it's some value y, some matrix y, or vector y. And then this would be y1 plus, or 2/3 y1 plus y2 is equal to 7. Of course, you solve this, you get y1 is 9. And you get, that's 2/3 of 9 is 6 plus 1 is equal to 7. So y2 would be 1. Yay. And then you just plug these guys, you see, you plug them in, and then you say, okay, well, that's the answers to those equations there. And what do I do with those guys? Well, if that's true, then and now you've got U times x is equal to y. We said that, right? And then x is the values that I'm trying to solve for now. And so when I do this, I get so u, which is, what did I say u was? So it's going to be 3x1 plus 2x2 equals 9. And then I'm going to have negative 7/3 x2 is equal to 7. Not 7, is equal to 1, rather. So I get x2 is equal to negative 3/7. And this is just a gross problem. And then I'm going to have, so 3x1 minus 6/7 is equal to 9. This would be 63/7, so 69/7. X1 is 23/7. If I did it right. Now, this is ludicrous. The time you do all that, absolutely ridiculous. But I'm going to pretend for a minute that I'm going to do, I'm just going to go find my inverse matrix. So my inverse matrix is 1 over the determinant. So it'd be negative 3 minus 4 is negative 7. So negative 1/7. Looking good so far. And we're going to flip and switch. So flip signs and switch the places, right? So negative 3, positive 1, 2 and 2. No, flip and switch. Flip the signs and switch places, yes. So in theory, this should work, right? So it'd be 3, negative 1, 2, and 2. And then, so that should end up being the identity. Is that true? Okay, well, it's going to be negative 9. Uh-oh. Did I mess up? I did mess up. So it'd be negative 3 plus 4. Negative 3 minus 4 is negative 7. There we go. And then, yes, then for the bottom row times this column would be 0. And then the top row times the far column would be 0. And then the bottom row times that column would be negative 4 minus 7. There you go. So there's your identity matrix, yes? Cool. But I'm going to take this guy here and I'm going to multiply it by 9 and 7. And of course, at this point here, you're all laughing because no one would do it this way unless it was a 5 by 5, in which case, you're darn right I would do it this way, but this is what matrices were designed for, is to use calculators to do them. So it's negative 9 minus 14 is negative 23 over 7. And then negative 18 and then positive 21 is 3. So there's my answer. Boom, done. Bob's your uncle. So 23/7 and negative 3/7. See, that's how a normal person solves those. Okay, well, a normal person doesn't solve a 2 by 2 this way. But the point is, if you use that, it's just an easier way than doing it this other way. I am of the opinion that even if I had to do it the hard way, even if someone forced me to do a 6 by 6 by finding the inverse matrix, which again we can do that by doing a giant augmented matrix, then multiplying it out, okay, then after I've multiplied it out and whatever, I multiply it to the other side, I think that's easier than doing this U factorization business. That's just me personally. And so that's why I'm not going to bother teaching it that way. Okay? I guess it's as I say, a cute parlor trick, but have fun with it. So have a good week. Hope you're doing well. Bye.